Okay, Assalamualaikum and very good evening. Okay, today we will continue with our next lecture, which is on the EMC322. Okay, so previously we have learned on how we can plot uh, the root locus for the passive control system, and for today I will show you on the how we can plot the root locus for the active control system, which is involve a controlling of K, which is the proportional gains. Okay, so today, okay, so also we show on how that the K gains can affect the root locus plot for the different system. Different system means that this can be a second order system, third order, or the higher order system. Okay. Okay, so this is the overview for today class. Okay, the first one is on the general step of plotting the root locus. Okay, so basically you should know on to draw the root locus, okay, by sketching uh, from nothing to a complete of the root locus. Okay, so the next one is we are going to the MATLABs again. Okay, where the effect of K gains for the different system on how you can extract important information from the root locus plot. And also the last one is on the more comprehensive introduction to how from the root locus, when there are some question that ask you on to determine certain parameters of the root locus elements, so that you can use MATLAB to extract them easily. Okay, so as previously that been shown to you, okay, this is on the active control system, okay, which is considered as also the mass spring damper system. Okay, so this is a body diagram, okay, where you have the input force, and by including the active control elements, okay, so that you can reduce the vibration more effectively. Okay, so generally this is the equation of motion from the ODE. Okay, and then you can transform into the transfer function formula, okay, as has been introduced in my first lecture. Okay, so okay, this is the reduced transfer function diagram. Okay, where from this complicated body diagram we can reduce it to the more simplified form, where we can assume that sensor and actuator transfer functions to be a unity, which is equal to 1. And then for the controller for this lecture, we only consider as a K as a single gain, which is also we call it as a proportional gain. But later on in the next lecture, I will introduce you on how we can tune the control system more effectively by using the PID controls. Okay, so this is the transfer function. Okay, so you should already know how to derive it, okay, from this diagram. So this is the K gain that we can tune it to have a different plot of the root locus for the active control system. Okay, so the next one is on the general step, okay, to determine the root locus plot. Okay, uh, okay, so there's basically 7 steps. Okay, the first one, you must obtain the loci of the given transfer function. Okay, the loci means that you have to determine the poles and the zeros. Okay, so okay, so you should have know the poles, okay, the P and the Z. Okay, so from the given transfer function, you have a poles here, and also the the zeros, and also the poles. Okay, so you should know how to extract, okay, that value. Okay, so then you determine the numbers of asymptotes. Okay, this asymptotes is mean that the numbers of poles minus by the numbers of zeros. Okay, for example, you have 3 poles and none zeros. Okay, so that's is 3 minus 0 and equal to 3 lah. Okay, number of asymptotes. Asymptotes means that the projection line mean that's in your root locus how many asymptotes. For example, from this pole to these zeros, there's one, and then maybe it can generate another line. Okay, this is the second one. So for the third one, maybe it can generate another line from here to here. So this is considered 1, 2, 3, three asymptotes. Okay, the next one is to determine the angle of asymptotes. Okay, this is basically at the end of the slide you can refer the appendix for more details angles lah. Okay, but this is the equation of motion which is considered as a theta. 2x plus 1 divided by p minus z multiplied by 180. So the x is the is considered as from 0, 1, 2, 2 and so on lah. So for example, if you have 3 number of asymptotes, so that you must consider the calculation from 0, 1 and 2 only. This is considered as a 3. Okay, so we will get a different angles lah, okay, based on this x value. Okay, the next one is determine the centroid of asymptotes. Okay, this means that's a real poles minus by the real z. Okay, for example, you have a real p of maybe 0 and minus 2, and then this is must consider as 0 plus minus 2 and is equal to minus 2, right? And then is minus by zeros, there is no zeros, for example 0, and divide by p minus z maybe 3. Okay, so you will get the answer of as a centroid of asymptotes. Okay, I will show you after this on the more clear examples. Okay, so the next one we determine the breakaway points. Okay, where how from the two lines that meets and then they break away lah. For example, we have line number 1 here and line number 2 here. So at this point they are separate towards this roads and towards this road. This is what we call it a S break. Okay, which is breakaway points lah. Okay, there's another term we call a break-in point, where after going to the direction and then later on they mix again in somewhere of the points and they go into another direction lah. This is what we call it break-in point. Okay, so there's a breakaway where they spray away and there's break-in points where they meet again. Okay, so the first you have to determine the characteristic equations. Okay, remember this part. Okay, at the previous one. Okay, the characteristic equations. Okay, and then you must show it in terms of k equal to what. Okay, and then you have to differentiate it. Okay, dk over ds equal to 0. Okay, to get the in the form of this differentiation. Okay, later on you can calculate lah the breakaway points. Okay, the next one is to determine the intersection of the imaginary axis. So for example, for this locus, so you have this point of from the stable to the unstable regions. So this is the what we call the intersection of imaginary axis. So that you can determine the points where it's going to the unstable regions. Okay, this is important so that we know that at k gain equal to what value the system become unstable. The same method, you have to determine the characteristic equations, and then you can determine the value using the roots array as given here. This is the example you already learned in lectures by Dr. Zalila on the roots array, how to generate it. Okay, so basically when you have this array, so that you can get the range of plot k over 0 and towards the what is the value of we call it the k marginal, which is like for example b1, so that you can get the value of k from this uh, value, so that you can determine the intersection one. Okay, so another step is on the final one is to determine the angle of departure and arrivals. So this is basically involve the transfer function for the complex system. Okay, which is involve poles and zero, which is the imaginary parts lah. Okay, so I will not go in detail on this because at this level we are going to determine the values of the transfer function which non-imaginary parts only, okay, for the plotting of the manual. But for later on using the MATLAB, maybe you can use it easily lah. But for the sketch plotting, it's quite difficult. Okay, so let's see this example. Okay, so given the transfer function of the unity feedback system is this. Okay, and you need to plot the root locus diagram for the system. Okay, so this is the information that we get, okay, from the step by step of the how to draw the root locus. Okay, the step number one, to obtain the loci of the transfer function. So you know you have this uh, numerator and denominator. Okay, from the poles you know that there's two, okay, two poles, okay, this and this, okay, where you have the value of location s equal to 0 and s equal to -2. Okay, so you have two, okay, 1 and 2 here, and no zeros here. Okay, no s, no s, so it mean that's no zero lah. Okay, this is a 0. Okay, so to determine the number of asymptotes means that you minus p. Okay, 2 minus by 0, that's you get a value of 2. Okay, the next one is sorry, so the next one is on the determine the angles of asymptotes, okay, using these equations. Okay, as given before, define the theta. Okay, so since you have only two, the number of asymptotes, you use 0 and 1 lah. Previously I showed that if you have 3, so you replace the value of x with 0, 1 and 2, but this is have only 2, so 0 and 1 only lah. So we know that we only have two number of asymptotes. So for example, calculation when you replace with a number of with 0, so that you get the first angle is 90 degree, and when you replace with 1, so that you get the second angle is 270 degree. Okay, so the next one is to determine the centroid of asymptotes. Okay, the theta c here. Okay, so the real p minus by the real z. Okay, for example, you have a p with 0 and -2. Okay, 0 plus -2 minus by 0, no value of asymptotes for the real z, and minus by p minus z, which is a 2. Okay, so you get a -1. Okay, so this is the centroid of asymptotes. And the next step is determine the breakaway points. Okay, the s break here. The first one, of course, you going back to the characteristic equation. You still remember this characteristic equation, okay, at the denominator. Okay, hence we have a 1 plus k, so you include the transfer function of the system. Okay, 1 divided by s plus 2 equal to 0. So you do a solution here, you get this complete form, and then as explained before, you must show in terms of k, because we want to differentiate it. Okay, so by differentiate k by ds here, so that you get minus 2s minus 2. Okay, this is remove 2, and then the remaining part is minus by 2. Okay, so from this you can get in terms of s. Okay, so this is s break, we get a -1 here, so that we have a same value of breakaway points with the centroids of asymptotes. But in some cases, more complicated or higher order system, you will get a different value of s break and centroids. Okay, so step number 6 is to determine the intersection to the imaginary axis. Okay, you use the same characteristic equation that you determined before here. Okay, and then the second step, you determine the roots array. Okay, so you can arrange it by order. Okay, s2, s1 and s0. Okay, for the s2 you have the value of 1 here, and then skip the next one, which is k, you have a 1 and k. For the s power of 1, you have a value of 2 here. Okay, and you skip, there's no value, so that you put as a 0. Okay, you can have a solution here. 2 multiplied by k minus by 1 multiplied by 0 is 0. divide by the value of 2 here, okay, so that you get a k. So this is the end of calculation for the root array lah basically. But if you have a higher order, so there will be more step below, okay, as shown in example previously. Okay, so hence you can plot the k over than 0, and there is no k marginal because the equation have a direct solution at when x the power of 0, that the end is at this location, so that basically you have no k marginal, so that the system is stable and the root locus is not crossing at the imaginary axis. Okay, but in the higher order system, so that you can have a points lah. Okay, but for this simple one, there's no points at the imaginary axis. Okay, so we know that the system is stable and there's no intersection to the imaginary axis. Okay, so the next one is to determine the angle of departure. So we know that we don't have the complex form of transfer function in terms of pole and zeros, which imaginary parts. So that's we no need to proceed of this step. Okay, and now we have all the information to plot the root locus. Okay, so maybe you can see here. Okay, I can show you on. Okay, so from the information previously that you get, okay, the first one is on this. Okay, so step by step information. Okay, first you already obtained the loci, which two poles, the position is 0 and -2. Okay, so that's from this one. Okay, uh, okay, I can zoom a little bit here. Okay, so you have a 0 and -2, okay, for s1 and s2 here. Okay, uh, the next one is number of asymptotes. We should have two lines, okay, which is from 0 and from -2 lah. Okay, the next one is angle 90 degree and 270, so that you know the first line, okay, from here is going to 90 degree. Okay, and the second one, okay, so the second one is from the S2 here to the 270. Okay, that, but of course you have to determine the breakaway points first lah. Okay, and previously we have already determined the centroid of asymptotes, which is at -1, so that we can plot it theta c equal to 1 here. Okay, -1 and also the next step is the breakaway point also at the same points, which is s break is -1, so that we can show also the s break is at -1. So for this example, they are sharing the same points for the centroid and s break the breakaway points. Okay, so from this poles to the s break to 90 degree of angles. Second one from -2 poles, the S2 line towards the -1 breakaway point towards the 200 degree. Okay, the 270 degree. Okay, so for step 6, you know that the system is stable. Okay, there is no intersection to the imaginary axis. Okay, so that you can consider that when k equal to 0, you start from the 0 and also -2 going towards the k equal to larger value of positive larger value lah, which is we can draw it like this. Okay, so basically we don't have a k marginal, which is the plot will intersect at this location lah. So we don't have this point lah, so we just have this plot. Okay, this is basically the complete plot of root locus for this transfer function system. Okay, so as usual, you can always verify it, okay, using a MATLAB. Okay, so let's try. Okay, so for this one, okay, actually I just already done it. Okay, I just recall it. So the transfer function is 1, okay, and the below part is 1, 2 and 0. Okay, as you see here. Okay, so this example, actually you have the value of okay, the 1 at the above and the below one is actually when you has a solution of this. Okay, you will have a value of the system, which is the s power 2 plus 2s and plus 0 lah. There's no value here, so that's why we write it as a transfer function, which is equal to 1. Okay, 1 to 0 lah. Okay, so it become like this. Okay, so as usual you can plot it. Okay, so I just recall back the system is 1. Okay, 1 to 0. Okay, so you can confirm this value of transfer function. Also, as usual, you can confirm your zeros and poles value. For example, for the zeros, okay, there is no zeros. Okay, and for the poles, for the system, you get for the poles, get the value of 0 and -2 as what you have determined before in here. Okay, 0 and -2. Okay, so from that you can plot your locus. Okay, locus system 1, I consider as a system 1 here, and x is equal, so that you can have this plot. Okay, so this one you can verify back. Okay, you start from 0 here. Okay, and then is have another poles at 2. Okay, -2. So basically if you properly point it to this x point, you get a more accurate is -2 lah, and this is a the gate is 0 actually. Okay, so it's quite difficult to properly plot to point it at this location, because slightly move will give a different values lah. Okay, and of course the breakaway points here is the -1 and also the centroids. Okay, so that is how you can plot manually. Okay, so you can verify it using these codes. Okay, so on the next section, okay, how we can also generate or we can extract the information and the effect of k gains for the different system. Okay, for the case study number 1 is on the still under the second order system, on how you can determine the points of the root locus. Okay, so let's say the given transfer function is here. Okay, so that's from this you will have a solution of here, which is the s2 plus 6s plus 8. Okay, so actually you can also consider the system as a mass spring damper, which is this is the M, this is damping, and this is the stiffness. Okay, because it's the second order and here they have all the value of at each of the locations. Okay, but for this one is ask you on determine whether the s equal to -1, s minus 3.5, and s minus 3 plus 5j are on the root locus or not. Okay, so how you want to confirm it? Okay, you can have a solution. You can replace the value of s here. Okay, for example, for the s is -1. Okay, so previously you get the value of equation 1 plus the k gs equal to 0. Okay, so that's you move 1 here, so that the kgs equal to -1. So if any value that replace as a k can give a result of -1, so that's basically that's s value is on the root locus. Okay, clear? So for example, for this one you replace the value of s -1 to these two locations. Okay, so that you can have a solution of k divided by 3. So by see this, so that you know that this impossible for k over than 0, that we can get a value of -1. So that the conclusion is the s minus 1 is not on the root locus. But for the case number 2 and 3, -3.5 and -3 plus 5j, when you replace here, okay, and replace here, so you can get in this final form. So you know that by k is over than 1, for example, more than 0, which is for example 0.75, when you replace here, you will get the value of -1. And also this one, when the k is is 26, so you can also get a value of -1. So you can conclude that both s minus 3.5 and -3 plus 5j is on the root locus. So you can confirm it by using your MATLAB. Okay, it's using the transfer function. Okay, 168. Okay, as shown before here. Okay, both y is 1 and below part is 1, 6 and 8. So you can replot it. Okay, also using this another additional function s grid. Okay, you can also generate the s grid at the background lah. Okay, to show the damping ratio value. Okay, but this one you can confirm back. Okay, the number 1, the root locus is start from -2 and -4 here. Okay, and towards this point lah. Okay, this roots of the asymptotes. Okay, so you can confirm that 1 is not on the -1 is not on the root locus, -3.5 here in the root locus, and as the value going k is equal to plus large value, positive large value, for example 26 here, you can confirm that this also on the locus, but this is very limited because I want to zoom it to show on the detail value. It's quite difficult to show in the higher value because at this location also the value of k is just 5, but in 26 value it should be more higher than that. Okay, so the next one is on the third order system. Okay, this is the where you have the higher order system, and this the region in at the unstable plot that can be shown. Okay, so this is the third order system, and the question is we want to determine the unstable region on the root locus. So you have this solution. Okay, which is, you know that the poles is equal to -1, -2 and -4. Okay, and this is zeros. Okay, so the first step what you have to do is determine the plots. Okay, on the of the roots open poles and zeros. Okay, so this one you have know that there's a three plots, three poles and non-zeros. Okay, then the second one is determine the plots of the region of the real axis that lie on the root locus. So you know that at the real axis there will be three values of each is -1, -2 and -4 here. Okay, the number of asymptotes, okay, you get a 3 value of poles minus by 0, so you get the value of 3. Okay, then determine the angles and centroids. Okay, then you can sketch the asymptotes. Okay, so this you can show as previously, sum of the poles, which is -1 plus -2 plus -4. Okay, divide by zeros, down zeros, there's no zeros, so you get a value of 7. Divide by 3 here is -7/3. Okay, so this is example on how you can get a value of centroid is different from the value of breakaway points. Okay, so this is the table of asymptote angles. Okay, basically previously when you get a asymptotes number of 2, you will get a value of angle 90 and 270. When this in this case you have number of 3 poles, p minus z is 3, you will get a value of 60, 180 and 300 degree. Okay, so let's solve this. Okay, so the characteristic equation you can as usual, you can have on the solution. Okay, and for the point of marginal stability, okay, we know that division s theta plus j omega. So this is the unstable regions. Okay, so that by replacing the s to j and omega, so that you can have this solution. Okay, and then by uh, we can get finally on the solution, which is in this two form. Okay, so this one you can firstly solve the omega value. Okay, from this equation you will get the value of 0 and the square root of 14. Okay, and for the upper part, then you can replace the omega, this value, to this equation, so that you will get a k value of minus 8 and 90. Okay, so since the root locus is defined for only for the k is bigger than 0, so that we just uh, took only this value lah, the 90 lah. So we conclude the system become unstable for k more than 90. Okay, and the root locus we cross the imaginary axis at this point lah. Okay, so this is the one that I have done it. Okay, so the transfer function 1, the below part is 1, 7, 14 and 8. Okay, this is 1, 7, 14 and 8 here. Okay, you can plot this one. Okay, so you can confirm back there's 3 poles at here, -1, here -2, and here is -4. Okay, and you can also confirm, you tap at this imaginary axis at the intersection point, so that you get the value of 90. Okay, this is then if you can confirm it lah by plot it here and plot it here, so that basically this is below than 90 lah, this is larger than 90. Okay, so that's the example on how you can plot it. Okay, let's see another example here, the case study number 3, which is on the more higher order of the system, which is fourth order system, and how we can determine the breakaway or break-in points on the root locus. Okay, so the given transfer function for the unity feedback system is here. Okay, this is you can separate it right here like this. Okay, find the real axis breakaway and break-in points for the closed loop system. Okay, so the root locus has two real axis segments between the poles pair and between the zeros pair lah. Okay, we know that there's zeros at -6 here and -4, and the poles is start from -1 and -2. So from this we know that there will be two lines, asymptotes, they going in this way and another one is going to this way, and they meet again to go to the zero position lah. Okay, still remember that the root locus plot is start from the poles and will end at the zeros. Okay, so how to determine these two breakaway and break-in points. Okay, so we have the solution here. Okay, so remember that s theta plus j omega. So in this case we replace the s equal to the sigma, okay, because it's on the real axis here. Okay, so the equation, you can have the numerator. Okay, here the numerator, the above part. Okay, this is the numerator and this is the denominator. Okay, so here lah. Okay, you replace the s value with the theta. Okay, so the numerator, the upper part, and the multiply by the denominator, the differentiation of the numerator. Okay, previously you have this value. Okay, so the differentiation is 2s plus 3, and this one, the differentiation is 2s plus 10. Okay, so you can replace here. Okay, and then minus by the numerator. Okay, and multiply by the differentiation of the numerator part. Okay, so you will have a final form like this. So from this, by using the characteristic equation solution. So you can get the value of sigma 1 2 at minus 4.7 and minus 1.5. Okay, so this is actually the break in and breakaway points. So there is a calculation manually lah, but when you using the transfer function using the MATLAB, you can verify it. Okay, is 1 10 and 24 1 3 2 here. Okay, is 1 10 and 24, and the below part is denominator is 1 3 and 2. So you can have this plot. Okay, so you can tap in the points at this one. Okay, you get the value of 1.58 here and minus 4.71. So you can confirm this value is correct. Okay, so that's for this section. Okay, let's go to the final part of this lecture. In case I will show you on how a more detailed how you can extract the information from your root locus. Okay, so the given for the unity feedback system, okay, as this. Okay, so this is some question that later on can be asked, okay, maybe during your test or examinations, okay, on how you can extract the value of your root locus plot. Okay, the first one is on the plot the root locus diagram. Okay, basically that's the basic step. You must plot first, and then you can determine also find the imaginary axis crossing. Okay, for example, you have this plot. For example, what is the imaginary axis crossing? The gain value at this, what is the k value? See the breakaway points. Okay, for example, from this, okay, what is the breakaway points? The points and angle where root locus at uh, damping ratio equals 0.45. So by using the S grid, you can generate the line here where the damping ratio equals 0.45, and you can find the value here. Okay, so that you can determine the value, the points, and also the angles. Okay, the theta here. Okay, and find the k gain at the point where the locus cross. Okay, you can also extract the k value here. Okay, and finally you can find the range of k where the system is stable lah. Okay, for example, from k okay, from 0 to at this maximum point, that should be k is from 0 to which value. Okay, so that's all the critical information to analysis your control system lah, basically. Okay, so let's see the solution here. Okay, so I have already plotted. Okay, so you can use, okay, you have the solution at below part here. Okay, it's actually equal to, okay, the upper part is 1 here. This is 1 minus 4 minus 20, and the below part will be 1 s power of 2 plus 6s plus 8. Okay, so 1 minus 4 and minus 20 at numerator, and 168 at the denominator. Okay, so you can plot like this. Okay, and also you can generate the S grid, which is 0.45 to generate this line basically. So this is at damping ratio 0.45, so you can determine the information there. Okay, so the first one it asks you to plot the root locus. Okay, you should plot this root locus using MATLAB. Okay, using this codes. Okay, and the second one, find the imaginary axis crossing. Okay, so you can tap in at this point so that you can have a value of imaginary crossing lah, is a plus minus 3.1 I or j lah. Okay, so you get this value lah. This is actually 2 point here. This is plus, this is minus 3.9 I or j. Okay, the third one, find the gain k. So gain is given here is a 1.5. Okay, and the next one, find the breakaway points here. The breakaway points here, you can get the value of poles, 2 minus 2.88 here. Okay, the next one is on the find the points and angles where the locus is temperature equal to 0.45. Okay, so the first one is you have to find the the position, which is you have to use all this value, minus 1.53 plus minus 3.03j. Okay, and then the theta, okay, you still remember that is equal to this value, okay, the theta, okay, the theta equal to sine minus 1 damping ratio. Okay, so you will get this, the degree to 26.7 here, and plus 90 degree here, so you will get a 116.7 degree. Okay, the angles. Okay, the next one is find the gain K at the crossing point of, okay, so 0.45 here. You can directly get the K gain here lah, 0.417. Okay, and finally determine the range of the stable, which is of course the K will start from 0 to at this point, the maximum point, which is 0.5. Okay, so from this is how powerful of this root locus plot, that you can extract all the important parameters for your system. Okay. Okay, so the next one is on the similar question. Maybe you can try to plot by yourself. This is the example, another example, and try to determine all the important information from this question. Okay. Okay, this is the appendix that I have explained before on how you can draw the asymptote angles for the root locus. Okay, based on the table given, and also the degree. Okay. Okay, that's all for today class. Thank you very much.